Imagine 1,000 users opening an app at the exact same moment. Your server receives thousands of requests. What actually happens inside your machine? Does your server create thousands of threads or does it handle in some smarter way? To understand that, we need to look at how server architectures evolved. Because the way the server handles concurrency today did not start from where it is now. It evolved through several designs. Let's start with the most intuitive model. When a request arrives, the server simply creates a thread to handle it. That thread reads the request, performs whatever work is needed, and maybe calling a database or another service, and finally sends the response back to the client. From a developer's perspective, this feels very natural. One request, one thread, one response. And if you only have few users, this works perfectly. But things start to change once the number of requests increases. Now imagine 1,000 users arrives at the same moment. If the server follows the same model, it now needs to create 1,000 threads. And this is where hidden cost appears. Threads are not free. Each thread reserves memory for its stack. The memory used to store function calls and local variables while the thread executes. In many systems, that stack is around 1 megabyte. So if a server suddenly creates 1000 threads, it may reserve roughly 1 gigabyte of memory just for the stacks. And that's before the server even has started doing any real work. Clearly, this approach does not scale very well. So engineers looked for a way to control how many threads could exist at once. The solution was something called a thread pool. Instead of creating a new thread for every request, the server creates a fixed set of worker threads when it starts. For example, maybe 200 threads. When requests arrive, they are placed into a queue. Each worker thread takes a request from the queue, processes it, and then returns to the pickup next one. This approach solves the thread explosion problem. The number of requests is limited. Memory usage becomes predictable. But another problem quietly appears. And it comes from the nature of server workloads. Many server operations involve waiting. A request might need to query a database or call another service or read something from the disk. While the thread waits for that operation to complete, it cannot do anything else. It just sits there waiting. So even though server might have 200 worker threads, many of them are actually idle, simply waiting for I/O. And that leads to a strange situation. The server may have hundreds of threads, yet the CPU is barely doing any work. Most threads are blocked, they are not computing, they are just waiting. At this point, engineers started asking deeper questions. If most of our threads exist only to wait, why are we even creating them in the first place? The answer came from the operating system. Instead of repeatedly asking whether the socket is ready to read or write, the operating system can notify the server when something actually becomes ready. Modern kernel provides mechanisms like epoll that allows a program to monitor thousands of sockets efficiently. Instead of blocking a thread per connection, the server can register all sockets with the kernel and simply wait for readiness notification. And this leads to a completely different architecture. In this design, the server runs an event loop. The event loop waits for the kernel to report when a socket becomes ready. When a readiness event arrives, the server processes that request and then immediately moves on to the next event. Because the server only processes sockets that are ready. It never wastes time waiting. And this means a single thread can manage thousands of connections. This is the model used by systems like Node.js and many high-performance servers. But even this architecture is not perfect because eventually another limitation appears. Imagine the event loop receives a request that requires heavy computations. perhaps encryption or image processing or complex data processing. If the event loop begins executing that task directly, the loop becomes blocked. And while that computation runs, every other request must wait. So the event loop solves the problem of waiting for I/O, but it introduces a new risk when CPU work becomes heavy, and that leads to next architectural step. Modern servers combine the event loop with worker parallelism. The event loop continues handling network events and incoming requests. But when a task requests significant CPU work, the server dispatches that work to worker threads or worker processes. While those workers execute the computation, the event loop remains free to continue processing new events. This separation allows the server to scale across multiple CPU cores while still handling thousands of concurrent connections efficiently. But there is still one final challenge. Even the best architecture has limits. Imagine your server can process 1000 requests per second. Now imagine 10,000 requests suddenly arrive. Requests will begin to accumulate. Queues grow. Latency increases. Eventually, the system becomes unstable. At this point, the problem is no longer concurrency. The problem is overload. And the real system must protect themselves from it. This is where the idea of backpressure appears. Instead of accelerating and accepting every incoming request, the system begins rejecting excess load early. If the server is already operating at capacity, it may respond with an error like HTTP 429 too many requests. By refusing to process more work than it can handle, the system remains stable instead of collapsing under pressure. Backpressure is how modern systems survive extreme traffic. So, when a server handles thousands of users, it usually isn't creating thousands of threads. Instead, modern architecture combines several ideas: non-blocking I/O, event loops to handle network readiness, worker parallelism for CPU tasks, and backpressure to protect the system from overload. This layered thinking is how engineers design scalable systems, layer by layer.